or 17 minutes when we use the high order discretization. So some significant speed ups here. The results I've shown you so far all had rigid boundary conditions, but in reality, surfaces absorb sound when a sound wave hits them, and it does so differently at different frequencies. So we need to account for this frequency-dependent behavior if we want to do realistic room acoustic simulations. At the boundary, the relationship between the pressure and the particle velocity is fairly straightforward. In the frequency domain, it's related through the surface impedance here, or the surface admittance. We can employ a local reaction assumption, which assumes that there's no angular dependence of the surface impedance. This is generally taken to be an acceptable assumption where the sound propagation in the boundary domain is much lower than sound propagation speed in air. One good example is a porous material mounted directly on a rigid backing, and the porous material having high flow resistivity. Then if we use this local reaction assumption and inverse Fourier transform this to get to the time domain, we arrive at this relationship here, which is obviously a bit more complex than with this one here. We have a convolution integral that we need to solve, but we can employ what's called the method of auxiliary differential equations to solve this convolution, and this is what we have done. This method has some attractive features. It doesn't add a lot of cost or memory footprint to the simulation. It preserves the high order accuracy, and these material response functions can be captured with arbitrary accuracy. The way it works is that we map the surface admittance to a multipole rational function. We then inverse Fourier transform this and insert it into the convolution integral. And we arrive at this expression here, where we have these phi's and psi's, which are called accumulators, which are given by these auxiliary differential equations that we must then solve at every time step at the boundary. This way, we've managed to relate the pressure to the particle velocity through the frequency-dependent surface admittance in the time domain. We did a verification study here where we have a sound source emitting a sound wave and coming in abnormal incidence, hitting a porous material with a rigid backing and being reflected back, so a single reflection case. And for this case, an analytic solution exists. And we see that we get a very good match to the analytic solution, both in amplitude and phase. We also did some experimental validation where we measured and simulated a small room, which has 5 hard surfaces and 1 surface, which is this porous material mounted on the rigid backing. These measurements and comparisons were done by my colleague Tobias Cheol-Ho during his master project. And we see here that when looking at the frequency domain, we get a pretty good match between the measurement and the simulation. Another thing we investigated was curvilinear meshing. So as I mentioned before, when we use a high order numerical method, we can use a coarser mesh to solve the problem. And that's attractive from a computational point of view or an efficiency point of view, but it can reduce our ability to capture fine-grained details of the geometry because we're using larger mesh elements. But using curvilinear meshing can be a way to alleviate this, where we shift the nodes of the element to better fit the curved geometry. We did some tests on this, and this is one example where we simulated a disk, so a curved geometry, and look at the frequency response between the source and the receiver. And when we look at the frequency response, particularly here in the high frequency range, so let me zoom in there, then we see that when we use the curvilinear mesh elements, we indeed hit the true resonance frequencies of this disk. But when we use straight-sided elements, there is an apparent mistuning of the resonance frequencies. Another way to view it is to look at the error here. We see that the error increases with frequency when we use the straight-sided elements, it remains low when we use curvilinear elements. Okay, and last but not least, we implemented this solver into an open source framework called libparanormal, which is developed at Virginia Tech in the US. This is a highly optimized DGFEM framework for massively parallel multi-device computing architectures such as GPUs. This implementation work was led by my colleagues Anders Melander and Emil Ström during their master projects in close collaboration with me. The way it works is that we have a room here, and we divide the room into subdomains, and each subdomain is handled by a single CPU core. This CPU core is then linked to a GPU, which has thousands of cores, and thanks to the data locality of DGFEM, we can simulate each element in this subdomain in parallel on the GPU, And the only communication that needs to take place between CPUs is here at the subdomain interface. We did some performance analysis of this, where we see here that when we do multi-device scaling, that is when we use a system which has several GPUs, then we get excellent scaling properties. So in the ideal, we would have scaling equal to 1. That means that when we double the computing power, we halve the computation time. That is a theoretical impossibility because there's always some communication costs involved with parallel computing. But we see here, particularly for the case where we have enough data on each GPU, then we get excellent scaling properties. We effectively hide the communication costs. And this effectively means that we can simulate nearly arbitrarily large problems as long as we select our computing hardware in accordance with the size of the problem we're trying to solve. Just to make these numbers a bit more tangible, we simulated 2 large rooms, something that is meant to replicate an auditorium and a concert hall. These rooms have very low Schroeder frequencies, 28 Hertz and 20 Hertz, but we're simulating with enough resolution to be accurate at around or probably a bit beyond 1 kilohertz. And we see that using the system that we use, we can simulate the auditorium with 8 GPUs in around 1 hour and the concert hall with 12 GPUs in around 3 hours. And here, we're here at around 40 or 40 times the Schroeder frequency. Okay, so to summarize study number 1, we adapted modern state-of-the-art numerical methods to simulate room acoustics in the time domain. And we have shown that the high order accuracy is indeed very beneficial to reduce the computational cost when doing room acoustic simulations. We adapted a method for modeling the locally reacting frequency-dependent boundary conditions. We verified this against analytic solutions and against experiments or experimental data. We adapted curvilinear meshing, and we showed that this clearly improves the accuracy of the simulations when we have curved geometries. And finally, we implemented our algorithms for high-performance computing architectures, where we have demonstrated excellent multi-device scaling capabilities. So the main, perhaps the primary contribution of this study can be seen as to take these different modern state-of-the-art numerical techniques and bring them together in a coherent scheme that can be very efficient for room acoustic simulations. Okay, so this was study number 1. Now let's move to study number 2. There we focus more on the boundary condition modeling, and we go beyond this local reaction assumption, and we model the full extended reaction of the boundary conditions. This work is documented here in these 3 journal papers, and the motivation here is that room surfaces have a major influence on the acoustics of rooms, and it is important to model these properties accurately when we do room acoustic simulations. So what exactly do I mean when I say extended reaction behavior? So before we had this local reaction assumption, where we assume that there's no angular dependence of the surface. But in reality, most surfaces exhibit this extended reaction behavior where there is in fact an angular dependence of the surface impedance due to waves propagating here along the domain boundary. And this is particularly important for boundaries that have fluid layers or elastic properties. One classic example is the good old suspended ceiling, a porous material mounted in front of an air cavity, arguably the most common acoustic treatment in the world. This is known to exhibit strong extended reaction behavior. So we actually developed 2 approaches for modeling the extended reaction behavior in time domain wave-based simulations. And at the outset of this PhD project, there had been very little work done on this. So the first approach is perhaps a more approximate or phenomenological approach, which has the benefit of being very general, meaning it can model any type of room surface, as long as we know the angle-dependent surface impedance, but it is restricted to a sparse or low reflection density sound field, meaning it is mainly suited for modeling early reflections in larger spaces. The other approach is perhaps a more rigorous approach, where we actually simulate the sound propagation inside the boundary domain, and then we couple that with the air domain simulation. And the boundary domain that we worked with here is porous materials, so this is restricted to porous materials. Luckily, they are very commonly used in building design. But now the benefit is also that there is no sound field restriction. We can simulate the full impulse response. So I'll briefly describe both methods and show you some results. The phenomenological approach works in 3 steps. So first we do a sound field separation where we separate the incident part and the reflected part of the sound field using a wave splitting technique. Once we have separated the sound field, we can detect the incidence angle of the incoming sound wave, where it's coming from, and then we sort of continuously update the boundary condition or the boundary impedance, picking out the relevant impedance function depending on this incidence angle. We did a verification study where we have a sound source emitting a sound, hitting this boundary and being reflected back, so single reflection case, but the wave is coming in at different incidence angles. And for this case, an analytic solution or true solution also exists. We work with 3 types of boundary conditions or room surfaces, all porous materials, but of different thicknesses, different air cavity depths, and different flow resistivities. Absorber A1 here is probably has the sort of mildest extended reaction behavior, whereas absorber A3 has the strongest extended reaction behavior. This is very similar to a typical suspended ceiling. And if we look at the transfer function between a source and a receiver for a particular incidence angle, 65 degrees in this case, then we see that the red line, the extended reaction method we have developed, gives a much better match to the analytic or true solution as compared to using the commonly used local reaction assumption. If we compare the 3 different transfer functions, we see that we do best with A1 and worst with A3. This is because we have A3 has the strongest extended reaction behavior, where it sort of varies most sharply with incidence angle, and the wave splitting technique that we've employed is somewhat approximate, so it introduces some errors in the angle detection. So this is what explains these small differences here. But nevertheless, obviously a better match than the local reaction approach. If we look at the errors for all incidence angles considered, then we see indeed that when we use the local reaction assumption, we get large errors for the high incidence angles in all cases, whereas the errors remain low when we use the extended reaction approach. We also did some experimental validation where we compare against experimental data, which was collected during a previous study in the DTU Acoustics lab by Gunnarsdottir and co-authors. This is a photograph of their setup where they have a sound source and a receiver and the wave coming in at different incidence angles. So similar to what we had before. And now if we look at the transfer functions, now we only consider absorber A2, and we look at the transfer functions, we see that we get a better match to the measured data as compared to the local reaction approach. The measured data obviously has some fluctuations. This is perhaps due to diffraction effects because of the finite size of the sample, or due to loudspeaker imperfections, etc. But if we look at the errors for all incidence angles, then we see that their errors are lower when using the extended reaction approach. This was the phenomenological approach. Now moving to the domain coupling approach. So then we have 2 types of elements in our mesh. We have the air domain, where we solve these equations here, lossless wave propagation, as we did before. And then we have the porous domain. So this can be like a suspended ceiling, for example, where we solve different governing equations where we have some frequency-dependent losses in the wave propagation. And this is described by this equivalent fluid model that we use. And these are the governing equations in the frequency domain. The losses are determined by the material's effective density and the material's bulk modulus. But if we inverse Fourier transform this to get to the time domain, we arrive at these equations here, where we have some convolutions. We've already dealt with convolutions in the time domain. We used the ADE method, so we can do that again here. Allow me to show you how we formulate the equivalent fluid model in the time domain. If we consider the velocity equation, it looks like this, and we can replace the convolution integral with these ADE terms, where this accumulator here is given by this auxiliary differential equation. Then the whole system looks like this. So we have these terms here. This looks very much like the lossless case, but then we have these added terms here, which can be viewed as source terms or perhaps sink terms, which govern the frequency-dependent losses. They're given by these summations here, where these accumulators are again given by these differential equations here. So we have a coupled system that we must solve in the porous domain. we do the single reflection study similarly to what we did with the other one. This is comparing against an analytic solution, and through same absorbers that we used before, and we see, just like we did before, that the equivalent fluid model gives a much better match to the true solution or the reference solution as compared to the local reaction assumption. If we compare against the experimental data, then similar to what we saw before, perhaps a bit better error performance for the extended reaction method compared to what we had before, but indeed lower errors when using the equivalent fluid model over the local reaction assumption. Okay, so these results I've shown you so far were all for a single reflection case, but we also wanted to investigate, when we do full room simulations, what is the influence of modeling the boundary conditions, either with this full extended reaction model, or when we use simpler methods such as the local reaction approach, which is sort of the standard approach, one can say, for wave-based methods, or the field incidence approach, which is a weighted angle average. So it's similar to the commonly used random incidence approach, which is perhaps sort of the industry standard in geometrical acoustics. So we simulate 3 rooms, a hallway, a classroom, and an auditorium, where we have the ceiling of these rooms be the porous absorbers that we have worked with so far, and the other surfaces are frequency independent, absorbing with alpha equal to 0.1, so fairly reflective surfaces. And this is meant to replicate a sort of a fairly realistic or typical scenario. And we look at 3 parameters: the T20 reverberation time, the early decay time, and the C50 clarity parameter. And what we do is that we say that the extended reaction simulation, that's sort of our reference, because that is the most accurate simulation. And then we compute the deviation that these simpler approaches yield as compared to the extended reaction simulation. If we then look at the results, we see, in fact, that we get very large errors when using either the local reaction assumption or the field incidence approach in all cases, essentially. And if we just look at the averages here, then we see, for example, for the T20 reverberation time, on average, the local reactions approach yields around 19.2% errors. When we compare that to the just noticeable difference threshold, which is around 5%, you see that these are clearly perceptible errors. The field incidence approach reduces these errors somewhat, but still above the J&D threshold. The early decay time, then we have even larger errors. That is explained by the fact that the early decay time is a very sensitive parameter that depends on the accurate modeling of the early reflections. And for the clarity parameter, the error is now in dBs. We are above or around the J&D threshold as well. So the conclusion here is that, at least modeling these types of porous absorbers, we need to model the extended reaction. Okay, switching gears a little bit, but staying with the boundary conditions. So we also looked into uncertainty quantification, and I'll just briefly summarize this. So this work was led by my colleague Tobias Tidal during his master project, but in close collaboration with me. So we know that the input data has a high level of uncertainty associated with it. For example, the thickness of the porous absorber or its flow resistivity. And we wanted to try and quantify what is the influence of this input uncertainty on the outcomes of the simulations. So we had applied and adapted this framework of Roy and Oberkampf using this small test case here, which I've shown you before as our reference case. And very briefly, we basically found out that the input uncertainty is too high for the simulator to be able to predict common room acoustic parameters such as the reverberation time within these J&D thresholds. So just one example result here. So at 125 Hertz for a particular porous absorber and settings and source receiver position, the reverberation time is around 2.2 seconds, the measured reverberation time, and the J&D thresholds range then from roughly 2.1 to 2.3. So ideally, when we propagate all the input uncertainties through the model, our results should lie in this range. Then we're kind of accurate enough. But actually, the results lie in this range here, so from 1.7 to 2.7 or something. So well outside the J&D thresholds. So we need more accurate input data, is what this is implying. Okay, so to summarize study number 2, we developed a phenomenological method for modeling the extended reaction behavior of arbitrary surfaces. Show this to improve the accuracy of the simulations. We also show in the paper, which I didn't talk about here, that this is indeed applicable for modeling early reflections in sort of medium and large size spaces. We developed a domain coupling approach for modeling the extended reaction behavior of porous materials. We show this also to greatly improve the accuracy, and now there are no sound field restrictions. We did the quantification study comparing those different boundary modeling techniques, where we saw that using the local reaction or the field incidence approximation leads to large errors. For example, for the T20 reverberation time, the local reaction approach yielded around 4 times the J&D errors, and the field incidence approach almost 3 times J&D. We did experimental validation and uncertainty quantification, which is something I just briefly touched upon, but where we found that the framework of Roy and Overkamp is indeed well suited for this uncertainty quantification. And at least for the test case, we considered the input data uncertainty is too high. Okay, that was study number 2. Now going on to study number 3, auditory virtual reality. So auditory virtual reality is the idea of combining the acoustic model with the visual model, such that you not only hear the simulation, but you can also see the space at the same time. And the motivation from the building design industry is perhaps that acoustics can be a somewhat intangible or an unintuitive thing to work with. And this can be a way to make things more intuitive and easy to work with, particularly for non-experts, such as architects or clients and so on. And there exist some tools out there for creating reverberation or acoustics in virtual domains, but those tools are mostly aimed for video games and so on. So they're fairly low fidelity. They emphasize the performance much over the accuracy. So our motivation coming in here was that we wanted to develop a system that can actually use accurately simulated room impulse responses, for example, using a wave-based method, and couple that with the visual model such that we can actually use this for building design evaluation. So the system that we came up with looks something like this. The development of this system was led by my colleague Hermes San Pedro during his master project, but in close collaboration with me. We start with a room simulator where we pre-compute the acoustics, or one can say, or sort of bake the acoustics into the model. That is, we simulate the room impulse responses on a grid across the domain, and in each grid point spatial information is encoded into each impulse response using ambisonics. And during runtime, the user is kind of walking around the space or walking around this grid here, and is followed around by this virtual loudspeaker array. And then we have a VR platform that handles the visuals and does the position tracking. And then we have a real-time audio processor that handles the interpolation between the nearest grid points. It handles sound field rotation, ambisonics decoding, binauralization, etc. We did various listening tests to assess the quality of this system, but I'll just tell you about this one, the localization test, where we compared using first versus second order ambisonics, and we presented the stimuli under different conditions, presenting only the audio, presenting the audio but allowing head movement or head rotation, doing head tracking, presenting the audio and the visuals, and then presenting the audio and the visuals and allowing head movement. We studied the localization, that is trying to find out where sound is coming from in space, for 3 different rooms with different reverberation times, around 0.6 seconds to 2 seconds for a fixed position. If we look at the results, we see, first of all, that when we use second order ambisonics, we get better results than using first order ambisonics, so that's no surprise. Secondly, we see that the localization error decreases dramatically when we allow head movement. This is perhaps also not surprisingly. Now we can use perceptual cues that come when you move your head a little bit. Interestingly, we also see that when we just add the visuals, then we improve the localization performance. This sort of indicates the power of the holistics of virtual reality. And finally, if we allow head movement and present audio and visuals, we get excellent localization performance. And these results are averaged across the 3 rooms, but we found that they're very similar for each of the different rooms. Okay, we also did some case studies where we employed the system on cases in Henning Larsen. Let me tell you briefly about those. So the first case we worked on was this College of Business in the US, where there was an ongoing debate about the acoustic design of some of the smaller auditoriums there. And to facilitate the communication between client, architect, and acoustician, we set up a virtual mock-up of the auditorium. And in the VR, there were kind of 4 auditoriums side by side. They were same auditorium, but with different acoustic conditions. And then the user could walk between the different auditoriums and hear a lecture in the room. And this proved to be very useful for helping the client and the architect sort of get a better feeling for the different designs and what influence different design choices had, and helping them make informed decisions, essentially. We also worked with this case here, Uppsala City Hall, where we did a virtual mock-up of this large atrium space, and we used the virtual mock-up to assess what is the appropriate design goal for this space in terms of reverberation, and try out different acoustic treatments. One sample of an outcome from this was that we ended up designing these wooden frames, these sound-absorbing wooden frames, which are incorporated into the facade, that's a glass facade that surrounds the atrium space. And I personally think this is a very nice example of what can happen when we actually integrate the acoustics into the building design process. Then the acoustic treatment becomes a part of the architecture. Okay, and last case here was an architectural competition for a renovation project of an office building in Copenhagen, where we did a virtual mock-up of one of the open plan offices in that space. And the purpose here was so this was a part of the competition material from Henning Larsen. And the purpose here was to sort of demonstrate Henning Larsen's dedication to high quality indoor environments. And I will show you a video from this one. In the video, you see the user walking around the space, and with the click of a button, he can sort of switch various aspects of the acoustic treatment on or off. I should mention that this is meant to be listened to in headphones, so when we play it in this room, then obviously the acoustics of this space are added to the mix, so it can be difficult to hear the difference between different designs. And for you people on Zoom, well, I hope it goes through. Let's see what happens. Blue means it's on and black means it's off.
Nej, det var faktisk routinen, der var der. Fordi der er bygninger nede på Amager, så urstægter til Nordjylland, og det er vi udviklede.
Okay. So to summarize study number 3, we developed an auditory virtual reality system based on pre-computed spatial impulse responses and real-time playback engine. This way we avoid using these low fidelity real-time simulators, but it does come at the price of some lost flexibility. We can only do static scenarios and only pre-computed scenarios as well. We did listening tests to assess the quality of the system, where we, for example, found out that we obtained excellent localization when using second-order ambisonics with visuals and head movement. And finally, we applied the system on 3 cases in Henning Larsen, where the system received good feedback and was found to add value to the design process. Okay, last study here towards real-time virtual acoustics. So as I just mentioned now, when we do this static pre-computation approach, we lose some flexibility. So in the ideal, what we would like is for the designer to be in the VR, as kind of illustrated here, and can change whatever comes to mind on the fly and sort of hear the difference. So this implies real-time simulations, but achieving real-time performance and high accuracy is obviously very challenging. So this is sort of the long-term vision, we can say. And the contributions here are perhaps stepping stones towards this long-term goal. Due to time limitations, I will actually need to skip this part completely, but let me tell you a bit about this one here, where we are using what's called model order reduction to reduce or speed up wave-based simulations. So these are fairly established numerical techniques that can be used to reduce the cost of simulations when solving what's called parametrized partial differential equations, or when we're solving a system or simulating a room for many different parameter values. For example, when we're optimizing the room design, I mean, when we might want to simulate the room for many different surface materials or many different geometries, or when we do real-time virtual acoustics, we want to have moving sound source, etc. It does rely on this offline-online paradigm where we have an offline stage where we do sort of an exploration of the parameter space. We solve the full system or full simulation wave-based model for a few selected parameter values. And we take that data and we study that and we create a reduced model that can be solved much, much faster than the full model for a new parameter value that wasn't one of those sample values, but somewhere in between. We employ here the reduced basis method. Let me give you a very fast introduction to that. So we have a full order model here. This is a spatial discretization operator, can be a FEM or SEM discretization, and this will typically be a very large operator, perhaps in the orders of millions of degrees of freedom. We assume that there exists a reduced basis that can accurately capture the physics of this system under the variation of this parameter mu, with much, much fewer basis functions that or size of the domain of a discretization as compared to the full model. If we then insert this reduced basis into the full model, we arrive at this reduced order model, which we then solve for these time-dependent coefficients. And the discretization operator here now has a size of NRB times NRB instead of NFB times NFB. And hopefully NRB is much, much smaller than NFB. This will be case dependent, physics dependent, and so on. So yeah. The key question is, how do we actually determine this reduced basis? And we've been working with two basis generation techniques. A fairly standard approach called the proper orthogonal decomposition, which does a uniform sampling through the parameter space. And then we developed a novel data-driven greedy POD algorithm. So greedy algorithms, they don't sample uniformly in the parameter space, but instead they try and sample only the spaces that are most informative, or have the most informative data. And I'll just show you one example result because yeah, time is running out here. So here we're simulating a 2D domain, just a small rectangular domain. And the parameter that we want to be able to vary is the boundary impedance. So we want to be able to vary this value of the boundary impedance from 500 to 10,000. That corresponds to having an absorption coefficient from 0.15 to 0.9. So in the offline stage, controlled by the POD greedy algorithm, we sample for a few selected values of Z, around 10 or 15 values, simulate the full model for those values, and we take that data, we do a singular value decomposition of that data. If we look at the decay of the singular values, we see that if we select, for example, enough basis function to obtain 10 to the power of -3 energy here, then when we have around 360 basis functions in the reduced model, whereas our full model had a size of 1800 degrees of freedom. So the size of the reduced model is only 20% of the size of the full model. And if we now take the reduced model and simulate for any value here ranging from 500 to 10,000, these are two examples here, some values chosen outside of those initial sampling values, we see that we get a very good match to the full order model, but solving a system that's only 20% of the size. Okay, so to summarize study number 4, this part I didn't touch upon at all, but this was paper P7. There we compared two parallel implementation strategies of the image source method. So this is work towards our long-term vision of creating a geometrical acoustics and wave-based hybrid model where we sort of get the best of both worlds. But we found that it's case dependent which one is better. We applied the reduced basis method to room acoustic problems, and we saw a good potential for reducing the computational cost, at least in simple test cases. However, one important caveat was that we identified some stability issues in the reduced models. So when we do long time simulations, then sometimes this reduced model blows up. But then in the paper, we also showed that if we use what's called structure preserving model reduction, then we do ensure the numerical stability. This is sort of emerging model order reduction techniques from the applied mathematics community. However, implementing frequency dependent absorption, which is absolutely necessary in room acoustic simulations, is ongoing work in the structure preserving model reduction. So we kind of conclude that further research is needed on both wave geometrical hybrids, that's this work here, and on model order reduction. Okay, so to wrap up, in this PhD project, we developed a new type of time domain wave-based simulation scheme using state-of-the-art numerical methods. This scheme can simulate large and complex spaces well into the mid-frequency range within acceptable runtimes. We show that the high order accuracy is indeed very beneficial in room acoustic simulations. However, further development or optimization is always possible. So there are, for example, having directive sound sources and binaural receivers, improving the high performance computing aspects further, interesting topics such as domain decomposition, local time stepping. These are things that could be interesting to explore in the future. We developed methods for modeling the extended reaction of certain boundaries, and this worked very well. We also saw that modeling the extended reaction behavior is indeed necessary, at least for the porous materials we considered. An interesting future work could be to do a domain coupling approach to different types of boundary domains, such as vibrating panels or perforated panels. And we also saw that we need further uncertainty quantification of boundary conditions to sort of pinpoint the weak points in the input data. And almost certainly we need improved input data. Finally, we developed an auditory virtual reality system for static scenes. This works quite well, but the holy grail or the long-term vision is a system that has both high accuracy and high interactivity. And this can perhaps be achieved by using wave geometrical hybrids and or model order reduction. So I would just like to thank very much my fantastic and very supportive supervisors, and it has been an absolute joy to work with you for the last 3 years or so. I'd also like to thank all of the brilliant and talented master's and bachelor students who worked with me and us during their final projects. You all contributed greatly to this work, both directly and indirectly. Other close collaborators and co-authors, thank you very much. Everyone, past and present colleagues of the House of Acoustics, everyone in Henning Larsen, and friends and family. Thank you.
Thanks, Finnur. Excellent timing. So we will take a 10-minute bio break, and then we'll start again 10 o'clock sharp.
Yeah, exactly. It combines everything. It's like Henning Larsen design, a wave, and Iceland. So. Yeah, maybe Nej, jeg er faktisk Island. Okay. Jeg tænkte bare, jeg selv synes. Okay, men desværre kommer jeg for sent til det. Men var der nogen på Finnur som interesse med din afhandling? Jo. Det bliver offentliggjort på et eller andet tidspunkt. Men ja, det må du sige. Jeg ved ikke engang, hvad vi er det safe. Så har vi så kan du sige, at vi er en kollega der. Vi har været begge to med der på udviklingssektionen. Men også med udgørelse. Okay, ja. Det er jo også. Ja, spændende. Ja, det er også. Synes faktisk, det er tak for det. Ja, men skal du fortsætte med det her slags yeah, we're looking into that. Okay. There's some balls in the air, kind of what I'm trying to figure out which way to go. Yeah, that's what. Yeah, I think we'll proceed in one way or another. Yeah, but not for example, Lloyd. They want probably some more finished product.
Finnur, so to interrupt you, I was out of the meeting. Can you give me access?
I think you do that. Finn has to do the.
Oh.
Let me see.
I think it was organized.
Yeah.
You can see me waiting.
If I go here. I'll go get Finn.
Yeah.
I'm thinking more and more on it. At first, I thought maybe it's not that. It's more for the very in-depth questions, but maybe since I'm here, anyway, just let's see. Yeah. But I'm sorry I came too late.
I cannot join. Why is it? I mean, I'm a big here employee, so I'm supposed to get in the
People will join throughout the whole presentation. It's done, I found 2 minutes before.
Yeah.
To af dem er her, men en er på nettet, fordi han er fra Norge, og han kunne ikke, hvis han kom her, så var han nødt til at tage 10 dages karantæne. Så han besluttede at blive på nettet. Så han kom til
Ég er búinn að setja Aldís inn hérna sko síma. En hvernig tekja mikrofónin af?
Well done.
Okay. I think so. Yeah. Good news, okay. You got the plan? So, it's around 4 or 5 million. We were just 2 guys in there. Yeah. It's not enough for both of us, anyways.
I don't know, but you have time in your talk.
Yeah, we have to talk about that, exactly how we do it. But at least, I mean, it's good news. Yeah, that's something, so we're happy, you know. In the long run.
Actually, last time I also.
Okay.
Yeah, but that's one.
Yeah. He's coming to the meeting on my Zoom.
Okay.
Yeah, on Wednesday. We was going to talk tomorrow. You know, apparently.
Okay, but he's trying out here or?
No, yeah, he's coming on the Friday.
Jakob, you also have to log on to the Zoom session. To say something about
Cheol-Ho,
so
Most similar work.
So also we start methods and